last time we left off talking about an example with a car that had a mass of 1,250 kilograms, accelerated from 0 meters per second up to 60 miles an hour, so it's 26.8 meters per second. Okay, and we determined that the work involved with that was in the neighborhood of 450,000 joules. We then were told that if the time was 3.4 seconds, and the power is work over time. Okay, so 450,000 divided by 3.4 came to about 133,000, or 132,000, I guess, it's close. 132,000 watts. And then I asked those in the class who knew a little bit about cars that if that only converts to 177 horsepower, well, that's a very average amount of horsepower. That's the amount of horsepower my car has. My car will not go from 0 to 60 this quickly. So what's going on? And we decided that what must be happening is that there's some energy wasted. Okay. And when there's energy wasted, we have to introduce this new idea called percent efficiency. Percent efficiency, which gives us a numerical way to describe what portion of the energy that's being put into the system is simply being wasted. Say I'm riding a bike, I'm pedaling a bike. The input is the exact amount of work that my legs are exerting. So if I had some way to measure exactly how much energy my legs were burning, so that would be the work put into the system. So this is what my legs are, let's say, exerting. Okay. And it so happens I'm going to take the work output, and in the case of the bike, this would be the change in kinetic energy and the change in PE of me and the bike. So maybe I'm going uphill, maybe I'm increasing in speed, maybe both. But that is the output. Okay, so it's the observable effect of the work that's being done. However, because of friction and all kinds of stuff, air resistance, and simply other types of inefficiencies, we're not going to get what's known as 100% efficiency. So if we take output divided by input times 100, I will get percent efficiency. Okay, and interestingly enough, this equation works if you use power out versus power in. You still get the same percent efficiency. It's just you're adding sort of a time factor when you're putting in power, but it cancels out because you're dividing by another power. So let's do just a quick example of this. Let's keep with the bike analogy. So here is here's Mr. Ryerson riding a bike. As I do so often. And let's say the change in energy of the bike. So I go from, let's say, KE equals 0 joules, and some work happens, and then I get up to KE equals, let's say, 1,000 joules. Okay, so that would be the output. Right? I go from 0 meters per second up to some speed, which gives me kinetic energy of 1,000 joules. But imagine I've got this magic work meter attached to my legs, and I find that my legs put in 1,500 joules. Okay, so one question, a simple question to answer would be, well, how much of that energy is wasted? Okay, I put in 1,500, I only get 1,000 worth of stuff done, so that would mean 500 of it is wasted. If I want to know the percent efficiency of this, okay, well, I take the output, 1,000, divided by the input, 1,500, times 100. Okay, and this is going to come out to percent efficiency of about 66%, 66.66666, whatever. Okay, so that's sort of a simple example. Maybe a more practical example, and one that's a little bit different from the stuff we've looked at, but it's the same in principle. Say I have an electric motor. So here I have a plug in the wall, and I've got something plugged in to an electric motor that, let's just say it spins something. Okay? Now, if I know this machine has a percent efficiency, actually no, let me not do it that way. Let's keep it simple. If I observe this machine having an output of 550 joules. Okay, so I have this output of 550 joules. But then I look at the power usage for that outlet that day, and I find that 2,000 joules of energy left that outlet. So I got 2,000 joules of energy coming out of this outlet, and it goes down along this wire, goes in here, some stuff happens, and then I only get 550 out. Okay, well, we do the same thing. We put the work output, 550, divided by the input, 2,000. And this one I'm not going to be able to do in my head. I'll have to, actually, sure I can. It's going to be 0.225 times 100 to turn it into a cent. So 22.5%, I believe. And if you plug that into a calculator, let me go ahead and pull up a calculator here. So 550 divided by 2,000, 275. All right. So I was close. 275. So 27.5%. Okay. So this is the basics of percent efficiency, and would have gone through more examples in class, but this will give you a bit of an idea of what's going on, and will hopefully make it so that we haven't lost an entire day. Again, my apologies for missing class. Simply one of those days where I just had a brain fart, misread the schedule, whatever. I simply did not make it to class, apparently, obviously. So we'll see you guys next time, and don't forget the stuff you learned here about percent efficiency.